the press! Stop!
This is the moment every engineer fears. A split-second failure that leads to total asset destruction, or worse, human injury. Safety isn't a feature or an add-on, it is the most critical design requirement of your entire control system designed to protect lives and equipment when logic fails. In today's video, we will address how to implement safety in control system design using TwinSAFE.
Welcome back to ControlX Engineering. I'm Akil, and today we kick off our TwinSAFE series, your step-by-step guide to mastering safety using TwinSAFE safety products from Beckhoff Automation. Because TwinSAFE covers a wide range of concepts, this will be a multi-part series. We'll walk through everything in order, starting with Beckhoff's safety hardware, selecting the right components, then introducing you to the programming software, and finally ending with full commissioning and safety logic programming inside the TwinCAT programming environment. In today's episode, we will review what TwinSAFE is and look at the safety product offering from Beckhoff Automation, which covers the logic terminals as well as multi-channel safety input and output terminals, which come in both IP20 DIN-mounted terminals as well as field-mounted IP67 boxes for remote safety inputs and outputs. We will also explore the safe communication protocol, FSoE, which is an abbreviation for fail-safe over EtherCAT. So put on your safety gear and let's get started. Programming safety logic shouldn't be a headache, and that's where TwinSAFE shines. TwinSAFE is an integrated functional safety solution from Beckhoff Automation that allows us to build complex, fail-safe logic directly within the TwinCAT environment that you're already familiar with. By leveraging FSoE or fail-safe over EtherCAT protocol, TwinSAFE tunnels safety data through your existing EtherCAT network, eliminating unnecessary redundant hardwiring while meeting the highest global safety standards up to SIL 3 and performance level E. With FSoE, the communication system is part of a black channel. In industrial safety, the black channel principle is a concept defined in IEC 61508 and IEC 61784-3. It allows transmission of safety-critical data over a non-safe communication medium, like standard Ethernet cables, without needing to certify every single switch, router, or cable in between. Think of it like sending high-value diamond in a locked armored safe through a regular mail truck. You don't need to trust the mail truck or the driver, because the security is in the safe itself, not the truck. Safety over EtherCAT is a TÜV certified technology developed according to IEC 61508 and standardized internationally in IEC 61784-3. At the software level, whether you are managing a simple e-stop connection or a multi-axis robotic cell, TwinSAFE provides an intuitive graphical block diagram-based editor with certified safety function blocks to program the safety logic that protects both your operators and your equipment from the unexpected. To make sure you walk away with a complete understanding of implementing functional safety with TwinSAFE, I have broken this tutorial into a 3-part series. In today's tutorial, which will be part 1, we are going to deep dive into the TwinSAFE hardware ecosystem. I'll show you the difference between EL terminals for your cabinet and EP boxes for the field. We'll talk about the yellow architecture and how FSoE allows us to run safety data over standard EtherCAT cables without compromising on SIL 3 or PLE standards. In part 2, we move into the TwinCAT environment. I'll show you how to initialize a new safety project from scratch and navigate the available tools for programming. We'll explore the core safety function blocks to build our logic graphically. The best part, I'll show you how to use the TwinSAFE simulation mode to verify and debug your logic entirely in software before you even buy a single hardware component. Finally, we bring it to life. We'll take our simulated and tested logic and deploy it into a real-world test bench using one of the safety logic terminals from Beckhoff. And we'll use the EL1904 safe inputs and EL2904 safe output terminals. I'll walk you through setting the physical dip switches, mapping safety alias data, and performing the final smoke test with real e-stops and contactors to prove that the system works. Before we jump into the hardware, I wanted to give you a glimpse of what a TwinSAFE safety programming actually looks like. It is as simple as dropping these yellow certified safety function blocks, which can be linked to the input and output channels of the safety I/O hardware. Let's take a closer look at this section here. On the left side, we have a safe OR function block with inputs tied to 3 normally open momentary push buttons. The outputs of the function block is tied to the restart input of the safe e-stop function block. The safe e-stop function block has several inputs from various safety inputs. The outputs of one function block can be linked to the input of another simply by connecting them with lines as shown here. This way, by using the various safety function blocks available in the TwinSAFE toolbox, complex safety logic like this one can thus be implemented, as we will see in part 2 of this tutorial. Today, our focus will be on the TwinSAFE safety hardware. If you have worked with Beckhoff products before, you may be used to the standard white terminals for the DIN-mounted components and the black and stainless steel IP67 and IP69K boxes for field I/O. They are fast, reliable, and great for standard control. But when it comes to human life and high-risk machinery, standard I/O isn't enough. Enter the yellow terminals. The most obvious difference is the color. Yellow indicates compliance with SIL 3 and PLE standards. That bright yellow housing is a global industry signal. It tells any technician opening the cabinet that this circuit is safety related. Do not bypass and do not treat it as standard I/O. But the real magic is on the inside. While standard digital input terminals like the EL1008 or EL1809 look for 24-volt signals to determine whether the input is true or false, the safety input terminals like the EL1904 isn't just looking for 24 volts, it's looking for clock signals. The terminal sends out unique pulses, clock 1 and clock 2, to the connected device like an e-stop. This allows the safety input terminal to detect short circuit conditions. It is a level of diagnostic intelligence that goes far beyond a simple high-low signal. Every yellow terminal also performs internal self-tests every time it powers up and while it's running. Let's head on to Beckhoff's website and navigate to the TwinSAFE product page shown here. Here you'll find information related to the TwinSAFE architecture, as well as links to the hardware and software. Today we'll be exploring the TwinSAFE hardware. On this page, you'll find all the hardware related to TwinSAFE. Using these filter options, we can narrow down the products shown to specific types. The TwinSAFE hardware comes in various shapes and form factors. There are DIN-mounted terminals, which come in 12mm, 100mm tall, and 68mm deep terminals. These terminals have IP20 protection rating, since they go inside the control cabinet. Some of them are dedicated logic terminals, like the EL6910 shown here. And some are dedicated I/O terminals like the EL1904, which is a 4-channel safety input terminal. There are also combination devices with logic and I/O built on the same terminal. The EL2904 is a digital safety output terminal with 4 channels. It switches 24-volt DC actuators with up to ½ amp per channel. Next, we have the IP67 style boxes for field devices. This one is the EP1908, which is an 8-channel safe input module with 2 channels in each 5-pin M12 connector. Next, we have specialized devices with built-in TwinSAFE logic, like this single-channel drive for 48-volt servo motors. It features integrated TwinSAFE logic for safe torque off and safe stop 1 safety functions. Speaking of motion devices, Beckhoff also offers optional safety modules, like this AX5801 option card for the AX5000 series servo drives, which enables the implementation of safety-relevant drive functions like STO and SS1. There are many more TwinSAFE devices in other form factors, but here I have listed the most common device types. Let's start with the TwinSAFE logic terminals. What is a logic terminal? In simple terms, it's a safety controller, which means it is a dedicated device that executes safety logic independently of your main PLC, and is the link unit between the TwinSAFE inputs and outputs. Instead of relying on the standard control task, all safety-related decisions, things like emergency stops, guard door monitoring, muting, or safe motion conditions, are handled inside the logic terminal based on the logic programmed by you. These terminals use certified function blocks to process safe inputs and generate safe outputs, and they communicate using FSoE over the EtherCAT network. They're designed to meet high safety levels, including SIL 3 and PLE, depending on the application. Some of the most commonly used logic terminals are shown on the screen. I've personally executed a lot of safety projects using the EL6900 and EL6910 terminals. Some of the features of the EL6910 are listed here. This terminal can establish 212 safe connections to other devices. What counts as a connection? A connection is one instance of a safe communication channel between the EL6910 logic terminal and another device. These can include safe input terminals, safe output terminals, drives with integrated safety modules, and remote IP67 safety modules. This allows us to deploy large distributed safety system with multiple safety islands and design complex machines with many safe I/O points. It is one of the reasons the EL6910 is considered Beckhoff's flagship safety controller. This terminal also features 128 TwinSAFE groups and allows up to 40 users. We will learn about groups and users in the next part of this tutorial series when we cover the software aspect of TwinSAFE. Also available on this terminal are certified function blocks that enable the safe processing of analog values and thus the implementation of even more complex safety applications. This feature was not available on its predecessor, the EL6900, which only worked with Boolean values. With the EL6910, you are no longer limited to simple on-off safety inputs. you can safely process analog values such as pressure, temperature, position feedback, speed, or torque signals, pretty much any type of continuous value. This opens the door to more advanced safety functions. Another highlight of the new controller generation with the EL6910 is the incremental download. In contrast to its predecessor, the safety project now consists of 4 components: logic, parameters, mapping, and info data, each of which has its own checksum. This means that when you make the change to your TwinSAFE project, you don't have to download the entire safety project again. Instead, the EL6910 allows you to download only the part that changed. The EL6910 also has diagnostic history directly on the component. All errors that have occurred can be read directly from the component and evaluated. The EL6910 also supports both ProfiSafe master and slave operation, which means it can exchange safety certified data with ProfiSafe devices on a Profinet network, in addition to its native FSoE communication. This makes the EL6910 a flexible bridge in mixed vendor safety architectures. TwinSAFE components have a published lifetime of 20 years, during which the target failure measures are guaranteed. The lifetime starts from the date of manufacturing according to the date code. The date code along with unique serial number are printed on the side of the terminal. And this has the following 8-digit format, where CW is the calendar week of manufacture, YY is the year of manufacture, SW is the software version, and the last 2 digits represent the hardware version. Here you can see all the conformity markings. For the North American market, the CUL US is an important marking, which means that the product has been tested and certified by UL to meet both US and Canadian safety standards. In other words, a device with the CUL US mark has passed recognized safety testing for electrical equipment in both countries, giving engineers and inspectors confidence that it meets the required safety and performance standards. Let's review some of the technical specs of the EL6910 logic terminal. It operates on 24 volt and requires approximately 160 mA, which it gets from the eBus. This is a purely logic terminal. It has no local inputs or outputs. There are, however, other combination terminals like the EL1918, which is a logic terminal with 8 safe inputs, or the EL2911, which has 4 safe inputs and 1 safe output. Its physical dimensions are the same as a regular EL terminal and weighs approximately 50 grams or 1.8 ounce approximately. These are the dimensions of the terminal when mounted on a standard 35 mm DIN rail. When installing inside a control cabinet, the recommended protection rating of the cabinet must be IP54 or higher in accordance with IEC 60529. Always protect the exposed electrical spring contacts with another terminal to the right-hand side or with an end cover, like the EL9011, to ensure the protection rating and for ESD protection of the device. During panel layout design, maintain minimum distances. Shown here are the recommended minimum safe distances between neighboring devices and the control cabinet walls. This ensures optimum convection cooling. If optimal spacing is not observed, the TwinSAFE components may overheat and could trigger shutdown of the affected components. The TwinSAFE components have a higher thermal waste compared to the regular non-TwinSAFE terminals, and it's a good idea to mix the terminals to prevent localized hotspots. It is also a good idea not to place the TwinSAFE terminals next to power supply terminals like the EK1100 and EL9410 as shown. This image shows an example of a thermally bad layout. Here, multiple TwinSAFE terminals are placed together, which may lead to the maximum permissible temperature of the devices being exceeded. The maximum permitted internal temperature is 95 degrees Celsius, above which the TwinSAFE terminals switch to safe state and report an error. The internal temperature can be read from the TwinSAFE component via its COE. Above this temperature, the TwinSAFE component automatically switches to the safe state called global shutdown and reports an error. Avoid doing this at all costs. Before you snap the yellow terminal onto a DIN rail, stop and look at the side. You will see a small block of dip switches. This isn't for decoration. It is the hardware key to your air safety system. Standard EtherCAT terminals are identified by their position in the lineup. If you swap two identical EL1008 input cards, for example, the PLC doesn't care. But in functional safety, position isn't enough. We need absolute certainty. Depending on the model, you will see either one dip switch block or 2 dip switch blocks, giving you enough combinations to assign a unique address to each safety device on the EtherCAT network. Devices like the EL6910 and EL2904 have single dip switch blocks with 10 switches labeled from 1 to 10, which gives us addresses from 1 to 1023 as shown in this table. Each FSoE address has to be unique and may only be used once within a network. Also note that 0 is not a valid FSoE address. These hardware set addresses are important because they prevent accidental mix-ups. Even if you move terminals around, download a new project, the safety controller can always verify that it's talking to the correct device. In other words, the dip switches give each TwinSAFE terminal a fixed tamper-resistant identity that's essential for safe communication. Personally, I always specify the FSoE addresses of the TwinSAFE terminals in the electrical design schematics. This way, the terminal gets the address set during the panel build process. During software commissioning, these addresses have to be validated in TwinSAFE, which we'll see in the next part of this tutorial. Like every other Beckhoff terminal, the EL6910 also has LEDs, which provide valuable diagnostic information about the state of the terminal. The top two rows have 4 green LEDs for status indication, and LEDs in the bottom 2 rows indicate diagnostics information. This table shows the meaning of the various state LEDs. A brand new EL6910 out of the box without a project will only have the state for green LED lit. Once a safety project is loaded and in run mode, all 4 LEDs are illuminated. Out of the 4 diagnostic LEDs, only diagnostic 1 LED is green and the other 3 are red. This LED indicates if the operating voltage and results of the internal tests are in valid range. If it is off, then the exact error code is indicated by the number of flashes on diagnostic 2 red LED. This table lists all possible fault types. Diagnostic 3 and 4 LEDs indicate fault states of both of the internal microprocessors. Ideally, you want all red LEDs to be off. Note that a global shutdown temporarily disables the TwinSAFE controller. This error can be reset by switching the power to the terminal. However, a global fault permanently disables the TwinSAFE controller, meaning that it has to be replaced. When diagnostic 1 green LED is lit, the error code is determined by the number of flashes of the diagnostic 2 LED. This table lists the possible flashing codes and their descriptions. These are usually not serious issues and related to problems with the logic implementation, communication error, or function block related errors. This table lists the possible fault states when diagnostic 2 is flashing and diagnostic 1 green LED is off. As you can see, these faults are more serious and related to voltage and temperatures not being within valid range. If you're wondering what the flashing looks like, it's a square wave with 400 milliseconds on and off and a 1-second pause after the flash code. And then it repeats. So to determine the error code, wait for 1-second pause and start counting the flashes that follow. Then refer to the table for the exact error code. If you're wondering where you can find all this information, don't worry. It's all neatly provided in the EL6910 instruction manual, which can be downloaded from the project page on Beckhoff's website. Since these are all safety devices, Beckhoff also provides all certifications and safety approvals available for download. This is the TUV certificate for the EL6910 and can be downloaded from the Beckhoff product page. The EL6910 can be considered to be the brains of the safety operations, but a brain is useless without sensors. To read the physical state of the connected safety devices like e-stops, light curtains, etc., we need the EL1904 safe input terminal. This is a 4-channel safe input terminal that serves as a TwinSAFE FSoE slave. It operates on a 24-volt DC basis, but that is where the similarities to a standard input card end. The EL1904 is engineered for high-risk applications. Like the logic terminal, it is also certified by TUV to meet SIL 3 according to IC 61508 and Performance Level E or PLE according to ISO 13849-1. The EL1904 has 4 fail-safe input channels and accepts potential free contacts. What this means is that instead of accepting external 24-volt signals like a regular digital input terminal, the EL1904 monitors contacts like those of an e-stop. I will explain the exact mechanism in a little bit. The EL1904 also has 4 green LEDs to indicate the status of each of the 4 input channels. This terminal also has 4 diagnostic LEDs. Diagnostic 1 green LED indicates normal operation and should always be on, which indicates that the EL1904 is functioning correctly. If this green LED is flickering rapidly, it indicates various error conditions depending on the number of flashes. Diagnostic 2 LED illuminates red if the terminal detects an external supply or on cross-circuit detection. This LED turns off once the error is rectified. Diagnostic 3 and 4 LEDs flash to indicate other types of serious error conditions like over temperature, over voltage, etc. The diagnostic 4 LED indication starts with rapid flickering followed by first slow sequence indicating the error code and then a second slow sequence indicating the error code argument, as shown here. The flashing code is repeated after the second slow sequence, which is again followed by rapid flickering. The full list of error codes can be found in the product manual. I also wanted to point out this warning from the product documentation, which states that modifying any of the COE parameters of TwinSAFE components in TwinCAT will render that terminal useless. These objects contain safety-critical information such as device identity, safety configuration data, checksums, FSoE communication parameters, and other certified safety logic behavior. As these objects are part of the terminal safety certification, They are not meant to be modified by the user. Any modification is seen by the TwinSAFE device as tampering and immediately locks itself into a permanent fail-stop state. In short, all device configuration must be done through the TwinSAFE workflow and not by editing CoE objects directly. The inputs 1 to 4 can be connected to either normally closed or normally open contacts. We can make the appropriate logic decision when we program the safety in the next tutorial. The connection points accept wire size from 28 gauge to 14 gauge. I highly recommend using wires terminated with ferrules, which can easily be inserted into the terminal point. Also keep in mind that the wire length should not exceed 100 meters or 328 feet. These connection points are spring actuated and require an insertion tool like this one from Beckhoff. You can also use any flat 2x40mm screwdriver. The wire length restriction is because the EL1904 inputs use test pulses for cross-circuit detection, as well as to detect shorts to 24 volt or 0 volt. These test pulses are a built-in diagnostic feature that continuously verifies the integrity of your safety wiring and devices. They're essential for achieving the EL1904 certified safety level. Also note that the connection points labeled as input plus and shown here highlighted in red are actually outputs for the test pulses. The connection points labeled as input minus are the actual inputs for those channels. The test pulses are generated separately for each channel in order to be able to detect short circuits between the individual channels of a terminal and also between channels of different terminals. In order to generate test pulses as shown in the diagram, a software setting in TwinSAFE must be set to true for the respective channels. The test cycle for all 4 channels is typically 4 milliseconds. The times between the test pulses of different channels vary, thus allowing better diagnostic detection. I do want to point out that sometimes it might be required to disable these test pulses, for example when connecting sensors with a 24 volt output. In such cases, the 24 volt signal can be connected to the input minus connection point of the channel and disable that channel's test pulses in TwinSAFE by setting the corresponding channel's index value to false. To achieve the safety category 4, 2 input channels of the EL1904 must be assigned 2 different switch contacts of the same device, either 2 linked NC contacts or a linked NC and NO contact. In TwinSAFE logic, a test of discrepancy between these 2 signals must be set up. In this example, I've set up a discrepancy of 100 milliseconds between the 2 channels. If the 2 NC contacts don't open within 100 milliseconds of each other, this will cause an error. On the EL1904, the TwinSAFE address is set using the 2 8-position dip switch blocks on the side of the terminal. Together, these switches define the terminal's unique FSoE address, which the logic controller uses to identify the device during safe communication. Because the address is set in hardware and not software, it provides a tamper-resistant identity that stays with the terminal, even if it is moved, replaced, or the project is reloaded. Each switch position represents a binary value, and by combining 2 8-bit blocks, you can assign a wide range of valid FSoE addresses between 1 and 65,535. To ensure every safety device on the network is uniquely and securely identified. This table shows the switch positions and the corresponding FSoE address. We have processed our logic in the EL6910 and read our sensors with the EL1904. Now we need to take action. This is the EL2904, a 4-channel fail-safe digital output terminal. If the EL1904 is the sensors, the EL2904 is the muscle. It is the component that physically controls safety-critical actuators safely and reliably. Fail-safe means that the terminal will automatically switch off if it detects any kind of internal or external fault. The EL2904 is designed to switch 24-volt DC loads up to half amp per channel. While that might seem low, remember that these aren't meant to power a massive actuator directly. They are meant to drive the STO or safe torque off inputs of a VFD or the coils of safety contactors. Like the rest of our lineup, it is certified for SIL 3 and performance level E. What does this mean, you ask? It means that the EL2904 is designed and certified to achieve a very low probability of dangerous failure, be used in high-risk industrial safety functions, integrate into a TwinSAFE safety system with confidence, and supports applications requiring Category 4 PLE, which is the highest performance level for machine safety. Some practical examples where SIL 3 is appropriate are emergency stop circuits, safety-rated outputs controlling actuators, guard door interlocks, safe shutdown of hazardous motion, etc. To conform to these safety and performance levels, the terminal uses a combination of redundancy, diagnostics, fault detection, and fail-safe behavior. Here how it works under the hood. Each of the 4 outputs is a fail-safe output, meaning the output is designed so that any internal fault forces it into a safe state, which is the off state. The terminal performs continuous self-monitoring to detect dangerous failures. This is a core requirement for SIL 3. The EL2904 continuously measures the output current on each channel. This allows it to detect short circuits, cross circuits between channels, load faults, and output driver failures. If the measured current does not match the expected behavior, the terminal forces a safe shutdown. The terminal supports test pulses and output channel testing that can be enabled via safety parameters. These tests detect stuck on outputs, stuck off outputs, output transistor failures, and wiring faults. Thus, this diagnostic coverage is essential for SIL 3 and Category 4. The EL2904 does not store its own safety parameters. Instead, they are downloaded from a safety logic device at startup. This provides verified and validated safety configuration, protection against tampering, guaranteed startup state, and cyclic safety monitoring via FSoE. FSoE ensures CRC-protected communication, sequence counters, timeout monitoring, and safe state enforcement on communication loss. This communication integrity is part of the SIL 3 safety chain. If the terminal detects internal hardware faults, communication faults, parameter mismatches, or diagnostic failures, it automatically switches off its output, which is the fail-stop behavior. This ensures that no single fault can cause a dangerous output state. To meet the Category 4 PLE, the terminal is designed to tolerate any single fault, detect most faults immediately, and prevent accumulation of undetected faults. This terminal achieves this through redundant internal monitoring, continuous diagnostics, and safe shutdown on any anomaly. The EL2904 uses Beckhoff's standard compact terminal housing, but in the wider 24mm format, because it contains 4 safe output channels and the associated power electronics. The housing is made of polycarbonate like the other terminals and is designed to mount on a standard 35mm DIN rail using the standard Beckhoff locking mechanism. This diagram shows the 4 output channels. As you can see, the output connection points reside on the right half of the terminal. For wiring, the EL2904 supports solid, standard, and ferruled connections with wire sizes from 28 gauge to 14 gauge, depending on conductor type. When connecting a single actuator via its own continuous cabling, the maximum permitted cable length is 100 meters or 328 feet. The EL2904 can safely drive actuators such as relays, contactors, guard door interlocks, signal lamps, etc. Each output channel can drive a load with 500 milliamp max. Like the EL1904 safety input terminal, the EL2904 also uses test pulses and output channel testing, as I mentioned earlier. This diagram shows a typical test pulse chart for the 4 outputs. The parameters current measuring active and testing of outputs active should be enabled in TwinSAFE. The EL2904 briefly injects control test pulses into the output circuits to verify that the output transistor can switch correctly, the wiring to the actuator is intact, no external fault is present, and that the measured current matches the expected behavior. This is part of the terminal's fail-safe design. If the tests detect anything abnormal, the EL2904 will immediately switch the affected channel to a safe state. The EL2904 uses signal LEDs on the left half of the terminal to give you immediate visual feedback about the state of each safe output channel. Each of the 4 safe output channels has its own LED, and these LEDs reflect the output on-off state. The terminal also has 4 diagnostic LEDs. If the terminal detects a wiring issue such as short circuit, cross circuit, or abnormal current draw, the LED may flash or switch to a fault indication pattern. This works together with the EL2904's integrated current measurement and output testing features. If the terminal enters a fail-stop state due to an internal or external safety fault, the LEDs help identify which channel has triggered the issue. Diagnostic 1 green LED indicates the state of the TwinSAFE interface. Diagnostic 2 red LED indicates the fault state of the digital outputs. The number of flashes indicates if there is an error at one of the output channels, if the voltage is too high or too low, as well as faults regarding internal temperatures. Diagnostic 3 and 4 red LEDs indicates internal terminal errors. These errors lead to shutdown of the terminal and it must be checked by Beckhoff or replaced. As I mentioned for the EL1904, do not modify any COE parameters on the EL2904 as well. Any modification is seen by TwinSAFE as device tampering and immediately locks itself into a permanent fail-stop state. On the EL2904, the TwinSAFE address is set using a 10-position dip switch block on the side of the terminal. This defines the terminal's unique FSoE address, which the logic controller uses to identify the device during safe communication. Each switch position represents a binary value, which allows us to assign a wide range of valid FSoE addresses between 1 and 1023. To ensure every safety device on the network is uniquely and securely identified. The addresses have to be unique for each TwinSAFE terminal in a network and should not be repeated. Also, as I mentioned earlier, address 0 is not a valid address. This table shows these switch positions and the corresponding FSoE addresses. Next, I want to highlight a few special TwinSAFE modules which combine logic and I/O on the same terminal. The EL2911 is a safe potential feed terminal for the power contacts. In addition, it has 4 fail-safe inputs for sensors with potential free contacts for 24-volt DC and 1 safe output with 10 amp driver. This terminal also features integrated TwinSAFE logic functionality similar to the EL6910. With the help of locally available inputs and outputs, a complete safety application can thus be realized directly on this terminal. It also has a variant, the EL2911-2200, which does not have the logic functionality and is a pure I/O variant only. Next, we have the EL1918, which is a TwinSAFE terminal with 8 fail-safe inputs for potential free contacts. This terminal also has integrated TwinSAFE logic functionality, similar to the EL6910. Thus, it can also be used as a safety controller. In the default state, the EL1918 is a simple input terminal whose input signals are transmitted via FSoE to a TwinSAFE logic-capable component. It also has a variant, the EL1918-2200, with 8 fail-safe inputs without TwinSAFE logic functionality, and is thus a pure input-only variant. The next combination terminal I want to highlight is the EK1914. If this looks familiar, that's because it's a variant of the EK1100 coupler. The EK1100 is an EtherCAT coupler that enables formation of separate stations with any number of EtherCAT terminals that are automatically detected and individually displayed in the process image. The EK1914 combines the function of the EK1100 EtherCAT coupler with 4 standard digital inputs and 4 standard digital outputs, as well as a 2-channel safe input and 2-channel safe outputs. The EK1914 does not feature TwinSAFE logic functionality, thus a separate logic terminal will be required. Now that we have covered the DIN-mounted TwinSAFE terminals and the core safety logic components, let's shift our attention to Beckhoff's TwinSAFE EtherCAT box modules. These modules extend the TwinSAFE ecosystem directly into the field, giving you safety-rated I/O right at the machine, without the need for a control cabinet. These IP-rated TwinSAFE boxes are designed for harsh industrial environments where dust, moisture, vibration, and mechanical stress are part of daily operation. With their fully sealed housing and M8 and M12 connectors, they deliver safety functionality exactly where it's needed, while maintaining the same TwinSAFE workflow inside TwinCAT. The EP1908 and EP1918 are Beckhoff's IP67 TwinSAFE digital input modules designed for collecting safety-related signals directly in the field. Both modules provide 8 safe inputs for devices such as e-stops, guard switches, enabling switches, and light curtains, all communicating over FSoE. The EP1918 adds TwinSAFE logic functionality directly on the module, thus it can act as a safety controller similar to the EL6910 term. Both the EP1957 and EP2918 extend TwinSAFE functionality into the field with safe outputs and distributed safety control. The EP1957 combination module provides 8 safe inputs and 4 safe outputs, all housed in a rugged IP67 enclosure with M12 connectors for reliable operation in harsh environments. The EP2918 provides 8 safe output channels for directly switching actuators such as contactors, valves, and safety-rated devices, up to 2 amp compared with half amp on the EP1957. Both modules offer integrated TwinSAFE logic functions, thus allowing us to implement modular distributed safety architectures without relying on cabinet-mounted hardware. That wraps up the hardware overview for part 1. In the next part of this tutorial, I'll jump into TwinCAT and build a brand new TwinSAFE project from scratch, exploring the programming tools, working with core safety function blocks, and using TwinSAFE simulation mode and debug the logic entirely in TwinSAFE before any hardware is even purchased. Thanks for watching. If you found this video helpful, then please like and share. If there's a particular topic you would like to see me cover, then please drop your suggestion in the comments, and be sure to subscribe so you don't miss out on future content.